equals negative log of that product there, what I actually get is this here. pKw equals pH plus POH equals 14. So now you see how the dominoes are falling into place from that important Kw expression. So this is very nifty. Why? Because if I know the pH of a solution, I immediately know the POH. So if the pH is 7, what's the POH? 7. If the pH is 14, what's the POH? 0. Okay? What does that mean? If the pH is 7, let's think about it. Remember, it's a logarithmic scale. So if the pH is 7, what is the concentration of the H pluses?
Equals to the concentration of OH.
Correct. If the pH is 7. But the question is, if I've got a solution, pure water, and the pH is 7, what is the concentration of H plus? Well, pH is negative log H plus, so it's going to be 10 to the minus 7. Okay? So you must be able to convert between logs and exponents. Remember, logarithm is the inverse of an exponent. And this is log to the base 10. Log to the base 10, not log to the base e. Some students always use the natural log. That's not the natural log, it's log base 10. Alright, so let's soldier on. This is basically now, we now have the mechanics to really understand the pH scale. If the pH is less than 7, it's acidic. If it's more than 7, it's basic. And if it's equal to 7, it's neutral. In other words, if the pH equals to POH. Now this is a nice table, sort of showing what I just described, this interconversion between pH and actual concentrations expressed in moles per liter or moles per decimeter cubed. If the pH is 0, that's very acidic. The concentration of H3O plus is 1 mole per liter, mole per decimeter cubed. Why? Because pH is negative log H plus, and negative log of 1 is 0. You see how this works? So let's go to a pH of 10. If the pH is 10, the concentration of H3O plus is 10 to the minus 10. So you see, the bigger the pH gets, what happens to the concentrations? They get bigger or smaller? Smaller. Much smaller. And notice, we go from 1 to 10 to the minus 14. That's 14 orders of magnitude. That's why we need the logarithmic scale, so we can put these enormous variations in concentrations onto the same scale. Also, it's convenient, because to say, oh, the concentration is 10 to the minus 8, it's a little bit clumsy. It's easier just to say, oh, the pH is 8. You see that? Right. So that's the pH scale. Now we come back to this notion of strong and weak acids and bases. Strong acids and bases dissociate fully. They're ionized to completion. They have very, very high Ka or Kb values. Okay. The example we had was HCl. And here are some very strong bases. These are, of course, the alkali bases for groups 1 and 2. They're very strong too. They dissociate to completion. And of course, now the question is, okay, we're talking about strong acids and bases dissociating to completion or not dissociating to completion. Would be nice if we could quantify that. And we can quantify that because we've got this Ka and Kb. That gives us a number. And that number is going to tell you how strong or how weak an acid is, right? Okay. So this is an excellent way of doing it. So we can actually go into a laboratory and measure the Ka or Kb values for acids and bases at certain temperatures, and that's going to tell us, or give us some sort of a measure as to how strong or weak the acid or base is. So here we have some values, okay, some actual values. These are experimentally determined at 298 K. Have a look. So check the guys at the top, right? These are pretty strong acids. Hydroiodic acid, that's the Ka value, 10 to the 10. What does that 10 to the power of 10 mean? It means there's 10 to the power of 10 more products than reactants. Is that a strong acid? Yes, it is. It's dissociating to completion. So there's a lot more products than reactants. That's why we have a very high value. But look at the bottom of the table, phenol. Phenol is an organic alcohol, right? It's an organic compound. 10 to the minus 10. What does that mean? It means that we have a very low dissociation. of phenol. That means it's a weak acid. Now again, instead of talking about these Ka values, which you can see are pretty clumsy, right, 1.8 times 10 to the minus 4, 6.3 times 10 to the minus 5, you can express them as pKa values, which is more convenient. What is, it's again, you take the negative log Ka, you have pKa. So the negative log of that is minus 10. Negative log of 25 is minus 1.4. So what's the trend? The stronger the acid, the higher or the lower the pKa value, pKa.
The lower.
The stronger the acid, the lower the pKa value. The stronger the acid, the higher the Ka value. You see that? So again, it's a logarithmic pKa, it's a p function, it's logarithmic. It sort of turns everything upside down. So pKa, if you have a very low pKa value, it's very strong. And if you have very high pKa value, it's very weak. And the same thing for bases, right? So here we have a couple of bases. Here you can also compute the pKb value, right, from the Kb value. So all of these things are sort of linked together. You can tabulate them, and you have the same trend. So here we've got, for example, urea. These are some organic bases. There's ammonia, and these are the tabulated pKb values. You can see that the stronger base has the lower pKb value. So what have we learned? We've learned Ka, pKa, Kb, pKb, and those are measures of acid or base strength. Okay. So this is basically just to summarize. Basically, all I want to say here is that all these relationships sort of fit together. It turns out that Kw, the ion product of water, is equal to Ka times Kb, and that's why typically one would only tabulate the Ka value. Basically, don't worry too much about that. That's a bit of a confusing slide, but the take-home message is that when we talk about, if you look at a textbook, you typically, for a substance, only see the pKa value, right? But there is a relationship between pKa and pKb. If you add pKa and pKb, what do you get?
14.
14. That's quite remarkable, isn't it? Like 14 is a magic number in a way. But it's not a magic number. It comes from all these relationships of, and particularly from the ion products of water. Okay.
So Kw is always 14.
Kw is 10 to the minus 14. pKw is 14. Okay, right. So we talk about, and that's because of this beautiful relationship here, which you can derive. And that's what I've basically done here in this slide. Okay, so you can talk about the acid strength or the acidity or the basicity, strength or weakness, based on the Ka or the pKa or the Kb or the pKb value. But you can also do it in terms of percent ionization. This is much less important. I just mentioned it for the sake of completeness. But you can also, for example, go into a laboratory and measure the percentage of H3O plus ions in a certain acid, right, that's being dissolved. And you can express that as a percentage, and that percentage, which you can express as the degree of ionization, will also reflect how strong or weak the acid is. Okay, so that's just an alternative to using Ka and Kb. Now, just as an aside, we've been talking about monoprotic acids. These are acids that only have one proton available for, that gets donated. But of course, some substances like sulfuric acid, H2SO4, has two protons that are capable of being donated. All right, and we call those polyprotic acids. Right, these are acids with more than one ionizable hydrogen atom. And here are some examples. All right. Let's look at sulfuric acid, H2SO4, right? You can see that that's the first ionization step, and then you're left with HSO4, which is the conjugate base of H2SO4, but actually that's got another proton that's acidic or ionizable, there it is, and that's what you see in the second reaction. So this sulfuric acid, we would call it diprotic acid, diprotic, right? Phosphoric acid is a triprotic acid. You start off with H3PO4, it loses one proton, it loses another proton, it loses another proton. And for each of these ionization steps, you can measure the requisite Ka value. But then you have to talk about Ka1, Ka2, Ka3, because there's 3 ionization steps in the case of phosphoric acid, 2 in the case of sulfuric, and so on. Now, what do you notice is the general trend in those Ka values in that table? Let's look at all the Ka values. What do you see as a trend for these polyprotic acids? Anyone want to venture a guess?
As you continue to dissociate, the Ka values lower.
Correct. Very good. The first K, the Ka1 is always much higher than the Ka2, which is always higher than the Ka3, which kind of makes sense, doesn't it? You've got a substance that's got 3 protons that are all ionizable. It's easy to pluck off the first one, more difficult to pluck off the second one, and more difficult to get hold of the third one, right? So that's the way to understand it. And you can see that that's a trend across the board. And again, you can express these Ka values in terms of pKa, which is more as a matter of convenience. Because it's much easier to say the pKa2 value of carbonic acid is 10.33 than to say it's 4.7 times 10 to the minus 11. You know, it's a cumbersome number. That's another reason why people use P functions. Convenience, simple convenience. Okay, because these numbers are so cumbersome. Look at that. Okay, in fact, and here you see the Ka1 value for sulfuric acid is so large it can't even be measured. Okay, right. Now, let's talk about how we can measure the pH of solutions. Right, so let's suppose, let's start off with a very simple example. If I were to ask you, what is the pH? What is the pH? What is the pH? This is now the question. Of 0.1 mole per liter or mole per decimeter cubed solution of HCl. What is the pH? How are we going to proceed? Well, what do we know about HCl? Is it a strong or a weak acid? Strong. Very strong. Very strong. What does that mean? It means if I take HCl, is it going to dissociate to completion? Yes. So if the concentration is 0.1 moles per liter of HCl, what is the concentration of H plus or H3O plus?
Minus logarithm of the 0.1.
Yes, okay, but before we get to that step, that's correct. But what is the concentration? If the concentration, this is a very important point, if the concentration of the HCl solution is 0.1, what is the concentration of the H pluses in that solution? 0.1. Why? Because it fully dissociates, right. So to get the pH is a straightforward matter of saying pH equals negative log 0.1, and then you can solve it on your calculator, right? What would the answer be to that?
1.
Correct. Correct. Now things get complicated, as they always do. What if I were to ask you the following question? What is the pH? What is the pH of a 0.1 mole per liter? Remember, the capital M is the same as mole per decimeter cubed. Mole per liter solution of acetic acid. Acetic acid. Now, what's the complication here? Temperature assumes 298 Kelvin.
Acetic acid is a weak acid, so we have to use more formula than 1 liter.
Right. It would be. It's a weak acid. So let's unpack that. Because it's a weak acid. It doesn't dissociate to completion. So would this be correct? Would it be correct to calculate the pH of that solution the way that I've done for HCl? No, because it's not dissociating to completion. Most of it, in fact, is not dissociated. You have to take the Ka value into consideration to determine how much H plus there is. And this is how you do that. You always start off with the reaction equation. There it is, acetic acid, that's the formula, vinegar. Right, there it is dissociating, there's our equilibrium. okay? And we can set up the Ka expression for that. There it is. I mean, you've seen this before. So this is now the Ka expression for this reaction. Now, if it dissociated to completion like HCl, we could just simply plug in the value and get the pH, because if it dissociates to completion, the concentration of the acid is going to be the same as the concentration of the H+. Now in this case, we can't do that because it's a weak acid, and that's its Ka value, right? That's its Ka value. So what do we got to do? Well, let's unpack this for a moment. Right, let's unpack this for a moment. These two concentrations here, are they going to be the same or are they going to be different? The H3O, if I take the Ka expression, those numbers, are they going to be the same? Yes or no?
No.
Yes, because it's a 1-to-1-to-1-to-1 reaction. So the concentration, remember, this comes from, this Ka expression comes from this reaction over here. The concentrations are going to be the same. Now, we make a sort of, we fudge things a bit and we say, okay, the concentration of the acetic acid is going to approximately be 0.1, right? And so what you get then is, you get this expression here. Remember, we want to get the pH. So since these two numbers are going to be the same because of stoichiometry, we just write H3O plus squared over 0.1. We know that the Ka value is 1.7 times 10 to the minus 5. We solve for the H3O plus, right, which is just simply a matter of taking the 0.1 to the other side and finding the square root of that. And then you get basically the concentration of the H3O plus. And then what can you do? Once you've got this guy, you can get the pH, because pH equals negative log whatever we have there. And you solve. You plug that value in and you get the pH at 298 Kelvin. Now, I think what we're going to do is we're going to take a break, and we're going to come back and reflect on what just happened there. Okay, let's take a 5-minute break, okay? 5 minutes.
So, man. I don't think it is, but it might.
It's an inverse exponent.
Yeah, it can be used in
Yeah.
it's just useful. If you know this, if you want something in terms of C, you can rewrite it using a lot, and it's not true.
No, I've never seen it.
Have it like this, you want to put everything in. Just ask. You often want that, like, if you're trying to simplify it, because you don't want it in the target, and you're getting involved, because then you want to grow equal, which is a value. Your X, what? To X equals some other expression. You want to know what number to as a power.
Use log to find.
Hey,
it.
oh, okay.
Gotcha. I don't have the strongest on that. Do you guys know there's a microwave in this building? Like, you know, not here. No, no.
Next question.
I'm sorry,
And you don't only want one value?
So like everything, support and everything, everything.
Wait, hold on. You mean like the first time on PS4 instead of your PC?
And it's phone and obviously not playing your phone. Yeah.
Wait, yes?
Yeah, press